Okay, so both me and Gio have some slides on mass transfer and the things we are looking at. I'm going to say a couple of things about accretion disks, and Gio is going to say things about the response of the accreting star. So, well, I sort of assume everybody in general knows the process of mass transfer, but for those who don't know, mass flows from the overflowing star to the accreting star, and this mass carries angular momentum with it, and mass, of course. There's two situations. This mass can either directly impact the accreting star, if the minimal radius of the stream, or the distance, is smaller than the radius of the star, and then it would accrete as if there would be a disk at a radius of 1.7 r minus. This, you can calculate what that r minus is. It's the closest approach of the stream. If there would be a point particle, then it just goes like this. Or there is a disk accretion, and thus a disk forms around the accreting object, and then the amount of angular momentum that is accreted onto this object is the amount of angular momentum that a Keplerian orbit has at that radius of that star. Any excess angular momentum is then transferred back into the orbit via viscous mechanisms of this accretion disk. I'll come to that in a bit. Now, there's evidence for non-conservative mass transfer. That means that not all of the mass that's transferred from the donating object is accreted by the accreting object. Well, several studies, quite a lot of studies have shown that a lot of systems can only be explained if there is a significant amount of mass being lost and also angular momentum being lost. One good example of this are algal systems. Well, these are post-mass transfer systems, and a lot of them can only be properly explained by some fraction of mass being lost. And now again, this lost mass takes angular momentum with it, and this is something you can choose in binary C what that angular momentum is. In most cases, it's an isotropic. Well, how do you say this? Yeah, okay. From the accreting star, it takes the orbital angular momentum of that accreting star, and the mass that goes away there takes away that angular momentum. Now I emphasize this accretion disk because that's the thing I'm looking at. Again, it's a disk around the accreting star, and angular momentum is transported out while mass is transported in. That's the mechanism that makes these disks work. And these disks are in a binary system truncated at some point, and these are truncated at more or less 90% of the mean Roslope radius of the accreting star. And this is calculated in a while back by Ployce and Pringle. And this is truncated by tidal interactions of the donating star. And at this truncation radius, the tidal interactions dominate, and they remove angular momentum from the disk back into the orbit. And now we decided to look if there can be a significant mass loss from these accretion disks in order to lower the angular momentum that's being transported back into the orbit. Because if the disk loses mass in this process, then this disk, well, it won't be transported back into the orbit if the outflow of mass is strong enough, fast enough. So my plan is to make some models with Vader. It's a disk evolution code. It's with a grid. It's not SPH. And set up a circumstellar disk in a binary system. Now I'm not really doing the stellar evolution at the same time. I'm really only doing the disk evolution, and I should see if this is enough. But at least this is the start. We're going to just evolve this disk, truncate it at some point, have some angular momentum sinks. And we're then going to try to evolve some common systems that display this. And then I'm going to vary mass loss and the position of where this mass is lost from the disk. And mechanisms by which this can happen is thermal winds, radiation pressure winds, or magnetic winds. I'm not going to implement that exactly into Vader, but at least have some prescription in it that removes this mass. And then I'm going to look at the structure and evolution of this disk and how much angular momentum is taken with it. And with binary C, what I'm going to do is I'm going to evolve or look for the Rochelab overflowing systems and select those that have accretion disks to look at the population of systems that display mass transfer via accretion disks, and then look at their common properties, the average, things of that. And what I can do in binary C is then also vary the amount of angular momentum that's being transported back into the orbit. Instead of now 100%, I can try to vary this with a portion of mass taking a portion of angular momentum with it. And then also come up with a gamma factor, as I showed earlier, of the specific angular momentum that's being lost. And here, I just quickly did this. A lot of systems that do Rochelab overflow the first time do have mass transfer through a disk. So this is, at first sight, an interesting situation to look at. Yeah, and I do it with binary C with the Rochelab overflow code, and the documentation is located in the docs for this. Some useful functions that I use for logging this are listed here. Test for accretion disk is one, obviously, that I use, checking whether they are Rochelab overflowing. So I just want to have the start of this Rochelab overflow. I don't want to evolve it totally. I just want to find the situation where it begins to happen and the end of it. And so with these flags, I can do this. Later, it will go more sophisticated, and yeah, that's what I wanted to tell for this.
Okay, so I'm gonna take over. So as David said, basically I'm trying to study the response from the accretor to that accretion. So basically I'm using MESA models to do that. The big thing that I'm interested in is computing these two quantities here, zeta add and zeta ec. So zeta add is the fast response to accretion, the adiabatic response. So basically matter falls on the star puffs up or shrinks. Then after that, it's, thermal equilibrium sets in and this thing stabilizes to a different radius. I've been interested, I've done more on the slow response so far, but I'll come back to this. Basically, once you have this zeta add and this zeta ec, you compare that with the Rochelab reaction to the exchange of mass. So you need more information from the companion, and that's what binary C is going to compute, no MESA. And basically, depending on what happens, you may have runaway situations or stability again. And then once we have that correctly constrained, we can look at, we can input that in binary C. We can look at some episodic accretion things, etc. So what I do is that I compute MESA models, then I drop a small amount of mass in one time step, and I see how that accretion spike changes the radius. Then the second stage would be to compute an accretion episode. And so what you usually do, you just drop mass continuously on your star because it's accreting. In MESA, that's because it's discretized. That is basically a series of accretion spikes. So the question is, can we describe this long episode as the sum or the combination, the convolution of accretion spikes with some kind of comp. For the spike itself, there are several issues that I had to go through so far. When you compute MESA models and you stop the evolution, they're actually not at thermal equilibrium. So you kind of have to wait a bit for it to stabilize. So you have you have to impose some relaxation steps. When I say you drop a small amount of mass in one time step, well, what is a small amount? And how much can you drop in one time step? How much is, in the end, your total mass transferred is m dot times the time step? How do these two things impact the accretion spike? And then I'm interested in the radius to compute these zeta factors, but are other quantities worth monitoring in the accretion spike, like the surface temperature, maybe? Things like that. So far, I've not looked into that. And I have looked mostly at the long-term radius variation that's linked with ZX. So this is the technical part for MESA people. These are the things I use. I basically don't have any accretion or mass loss during my evolution, obviously. My time step is limited to 1 million years before the accretion and to much less after. I have put all the safety nets that I've been advised to use, especially by Warwick. Then once I stop the evolution, I use this dx dt NUC factor. So basically, you still compute the luminosity, you still compute the reaction rate, and you multiply them by that number once you want to change the composition. And that number I set to 0. So basically, I stop the evolution. I also use these two criteria here, max and min time step factor. That's basically how much you allow the code to reduce or increase the time step at each step. So basically, if both are 1, nothing changes. And my relaxation stops when my radius is not changing so much anymore. And in that case, I use 10 to the minus 9 solar radii as a change in radius from one step to the next. Once that is done, I do my accretion spike. So still no nuclear reactions, but I have some mass change and some time step. So here I drop 10 to the minus 3 solar masses, and I do that over 1,000 years. It's still one time step, but it's 1,000 years. And then the relaxation afterwards, I think I keep 1,000 years as the time step. No reaction, no mass change, and no change in the time step again. I go until I have the same constantness in the radius. Sometimes it fails. That's the thing I discussed a bit with Orman yesterday. The general idea is that I think it's a numerical issue. I'm not 100% sure. Well, actually, I'm pretty sure. It's a numerical issue in MESA. When I drop that mass and weight, sometimes my core abundance goes back up. And over time, we got to the conclusion that it is probably due to some remeshing near the core envelope interface, something like that. I know I can set the mesh to be constant. I have not tried that yet. To be fair, Avishai Gilkis also told me to do something like that a long while ago. I kind of forgot. Anyway, here's what I get. So I just picked one example. I have many others, but this one is the prettiest. So I have a 5 solar mass star. I evolve it until the core abundance is 0.4 from 0.7 with a 0.02 metallicity. M dot is 10 to the minus, during the accretion spike, is 10 to the minus 6 solar masses per year over 1,000 years, like I just showed you. On the left, I started plotting the radius. Well, it's the radius minus the final one as a function of time. 0 is when I start my accretion spike. Before that, it's the relaxation phase after I stop the evolution in MESA. I didn't plot anything from that evolution in here. So starting point here on the left is when I reach that core abundance and stop evolving the star, then relaxation here, spike, and relaxation again. This one works. I have no issue with reaching the final radius steadily. On the right, you have the log of the same thing all the time. The axis is wrong here, the y-axis, but it's the log 10 of that thing. And basically, you oscillate around the final radius. That's why you have these bumps on the log thing, log of the absolute value, I was saying. And you reach 10 to the minus 9. So what I measure here is the difference between the radius right before the accretion at t equals 0, that final radius here after the relaxation, and the final radius at the end of the post-accretion phase, and I compare them. I did that for some kind of grid of models. This plot here is log of the total mass I accrete versus log of m dot. So when you go up that graph, you basically increase the time step, and when you go to the right, you increase m dot. When there's a triangle, you have positive change in the radius. Yeah. And when you have a dot, a circle, you have a negative change. The distribution of these two things on this plot, I don't really like. I would have expected them to be nicely separated. And I think this is due to that error I mentioned in the relaxation thing. I didn't check every single point to see if I reached the actual final radius I wanted. Also, there's a mess up there for delta m 10 to the minus 3. Well, these points were supposed to be regularly spaced, and they're not up there. That's because I think something happened with the time step anyway, and it didn't want to accrete all that mass in one go. So it kind of rescaled the time step somehow. And I think I only implemented that thing of the time step being absolutely constant all the time, only after that, after I saw that plot. So I have to redo this and do it better. Anyway, the example I'm showing here was one of the normal ones, and what I'm going to show after that has been checked. So I tried to vary the mass, the quantity accreted, and see if the impact of that, varying also the solar mass, the stellar mass, sorry. So what you find here, sorry, this plot is not very beamer friendly, but well, you have a positive change in the radius for almost every case, for all the masses above 4. When you increase the quantity you accrete, that change in the radius is not linear. Sadly, I'd say I was kind of expecting that, but at the same time, I wish it were linear. There's one thing that is kind of weird. It's for the 3 solar mass star, where when you accrete only a little amount of mass, the radius actually shrinks. Well, the star shrinks, the radius goes down, and then it goes back up when you increase the quantity you accrete. So the explanation we kind of came up with Rob, I think is very unsure, but there may be some very slight surface convection in that star that you feel when you don't accrete a lot of mass, but you suddenly don't care so much about it when you accrete more mass, because, well, you get to reach through that convection, surface convection. Technically, I think all models have some surface convection because you have ionization zones there. I don't know exactly what we probe when we accrete less than 3 millisolar masses that we don't feel after that.
But you do see, when you look at not the point at 0, but the point just to the right of it.
Yes.
Other models also go negative there.
Yes, indeed.
Which suggests that may well be right. It's just that the relative mass of the convection zone to the mass of the star is probably smaller. So that's why it goes up more quickly. I don't know. I'm not entirely sure. But, well, they may all dip below 0 and then go up.
I mean, for the 3 solar mass star, what we see here is that if the mass of the convection zone is comparable to what we accrete, we have a solid mass that is like, wait, I can't see the chat right now. The chat blinked, so probably someone has some good idea over there about. I can't access it. Okay. I'll see later. Yeah, probably that. The point I wanted to make is if the mass of the convection zone is comparable with what we create here, it's 1,000th of the mass that is in the convection zone. That's quite a lot, I think, for a 3 solar mass star. Anyway.
Yeah, but yeah, that's true. But it depends on the response of the radius as much as anything else, and that doesn't necessarily depend on how much mass. So.
The radius would shrink only if we still feel more the convection zone than the radiation zone.
Yeah, well, the convection zone also then just moves outwards. So.
In this case, inwards.
Why would it move inwards?
Because the star shrinks.
Yeah, relative to the surface.
Anyway, I think this explanation makes sense because, yeah, you pointed out that thing at very low accretion rates, but also I have not probed less massive stars, which I should have done, and also very massive stars don't seem, they seem pretty unfazed by this. Yeah. Like the 20 or 30 solar mass star, everything's linear. And
so if you did a 1 solar mass star with a big surface convection zone?
I did not.
That would presumably look like even more extreme than the 3. Because that has
probably.
What's the mass in the convection zone of the sun? 0.1, something like that?
The mass of the 0.02.
0.0. Is that all that's in the sun?
Yeah, 2% of the mass. 30% of the radius.
Right, sure. But that's still a lot more than you're accreting. So
yeah. It could go all the way to 0.2 solid mass, 0.02. So see what happens. Anyway, so that was for the long-term variability when I do an accretion spike. The second thing I wanted to do is basically try to assess that add the adiabatic answer response by actually using the derivative here, or maybe right after the accretion, like the way the difference, basically use the height of the peak. That's the big thing. The height of that peak is clearly related to this zeta add. I'm not really sure how. I mean, what kind of math I should do with it to retrieve the correct d log r over d log m, but it's clearly linked. For the accretion episode, I've not done anything there yet. Well, you can see that what I've done is very preliminary so far, and the accretion spike part has to be understood better. But well, yeah, what I plan on doing is compute this convolution of a COM with various amplitudes, maybe depending on what you want to do with a spike. If the variation is linear, that would simplify the treatment a lot because you just have to do spikes in a row rather than episodes that have many parameters. But it will probably not be linear, so I have to also see what's the reason for the non-linearity. Maybe the small amount of mass you create in the first time step is going to change the reaction to the next ones, especially if you're, like we just saw, on a 3 solar mass star and you start accreting slowly. Yeah, so that's more fun for later. So the roadmap basically is the code for spike accretion. I should have added spike here. It's written. I have this numerical issue with the remeshing maybe to solve before making it automated. I will do a grid for main sequence mass transfer case A, including mass, XC, and metallicity, and then expand it to later stages. Write the code for the accretion episode. This is also interesting. Well, to do the other way, so to look at mass loss rather than mass accretion. It's going to be necessary, The good thing with mass loss is that you can also compare it with things like what Fabian mentioned yesterday, the z-scalings of mass loss. And hopefully I'll derive a prescription for binary C. That's it for me. Sorry. Yeah, that's my last slide.
So, what is it you want to compare with the metallicity scalings? I don't really understand them.
Well, you can, well, Fabian yesterday showed these scalings of mass loss with the metallicity.
Sure.
If we do a grid of models with various metallicities, once we have the whole machinery going for episodes and spikes, we could retrieve something like that, couldn't we?
Yeah, but that's a wind mass loss, and this is not wind mass loss. I mean, here you're just looking at the response of the star rather than anything else. But,
Yeah. Okay. Fair enough.
And there's one thing we saw. I don't know who it was. Sorry, I apologize. It could have been Fabian that showed it yesterday. When accreting material, there was a response of the convective core. Fabian, are you there? Are you alive?
I'm alive and muted here.
Good. I think you showed a diagram with the response of the convective core when forming a blue straggler. Is that right?
I think I haven't shown this yet.
Maybe I just looked through your slides and saw it. That might be.
Exactly. So I sent you some slides that I might be showing depending.
That well be. Sorry, I've been very jet lagged this week. So
no worries. No worries. Yeah.
But if you, maybe you could explain it when you do talk about it, then that'd be fine. But there was a response of the convective core, which wasn't quite what I expected. So normally you'd say the convective core grows when you accrete material. That's fine. So you get rejuvenation. But what Fabian showed was actually the convective core grows and then shrinks again, which presumably is some kind of thermal response. But maybe he can explain that.
Do you have
just in a few words. It's quite simple, in fact. So if you merge stars together, then you have something which is called tidal compression or turbulent compression. And so your merger product at the end will turn out to have a higher density and a higher temperature in the core compared to what it would want to have in equilibrium. And so this higher temperature will drive vigorous convection, nuclear burning, and then a stronger convective core. And so this is a thermal response then of the star to come back to equilibrium. It's driven by this tidal compression and by this enhanced burning.
But do you expect to see this for mass transfer? I mean, you mentioned mergers. That's quite a brutal event compared to mass transfer.
Yeah, so in a mass transfer event, I don't expect tidal compression. I mean, you're going to add a bit of mass, and yes, so that means the star has a higher total mass, and you're going to slowly increase the core temperature. But this tidal compression only happens really if one star merges into the other, so that you have an overlapping gravitational potential. That is sort of the requirement to have the tides actually compress material and not to sort of try to tear it apart, right?
So I guess what's important then is you mix more of the star, so you actually get more hydrogen down into the core. Now that'll be important, but then it settles back down to an equilibrium state. So the actual convective core is what we would have expected, presumably, or roughly that. It's just that you have more fuel.
That's right. So essentially, what it all boils down to in binary C is that you would need to modify the internal clock of the star accordingly.
Yeah.
So you want to compare, in fact, the star after this thermal relaxation phase compared to what was before to know how much mixing really has occurred. So you're not only interested in the mixing that happens in this dynamical event, but also during the thermal relaxation later on.
Yeah. Now, the good thing is that the new model grid that Gio's putting together should take care of that quite naturally. Provided you can do the mixing, it will then do the convective burning starting again from the mixed, the ingested abundance. So that's good. We just need to know how much of the star is mixed when you merge two stars or when you accrete a lot of mass, for example. So, okay. Do we have any more questions from the audience that's sitting at the back? No?
I actually have one for David, which was about Veda.
Mm-hmm.
So it's a 1D code, right?
Yes. Yeah.
And you said these disks go up to about 90% of the rush lobe radius.
Yeah.
Do you need to care about them not being circular anymore at that radius?
Possibly. But this is not something that will fit very well into Vader. I know there can be, very high eccentricities in the outer parts of the disk. For now, I'm not going to treat that. But this is something I do want to discuss with Elliot and on how to treat this or how to fudge this into